This aircraft has a problem no passenger jet has ever faced. Its hypersonic engine cannot get it off the runway. Its metal skin cannot survive its cruising speed. And the same fuel meant to power it may also be the only thing stopping its wings from overheating. At Mach 5, the aircraft expands as it flies. The airflow entering the engine can destroy the engine, and every safety system added for the passengers makes the heat problem worse. Yet engineers are trying to place 100 people inside it and cross the Pacific before their coffee gets cold. To understand how they plan to do that, you first have to understand why a Mach 5 passenger jet should not be able to exist. At 5 times the speed of sound, every part of an ordinary aircraft begins working against itself. The nose absorbs an enormous thermal load. The wings expand. Seals distort. Fuel lines heat up. And microscopic gaps between panels can become points of catastrophic failure. The aircraft does not simply fly faster. It begins trying to pull itself apart. And somewhere inside this machine, engineers want to place a pressurized cabin filled with human beings. Passengers breathing normal air, drinking coffee, watching the Pacific disappear beneath them as a journey from Los Angeles to Tokyo collapses from nearly 12 hours to roughly 2. But there is something important you need to know. No certified Mach 5 passenger airliner exists today. The beautiful aircraft shown in concept art are not finished products. They are the final destination of a much longer engineering campaign. What exists right now are the pieces. Experimental aircraft, combined cycle engines, heat-resistant materials, and decades of research into keeping a vehicle alive in one of the most hostile environments ever created by atmospheric flight. The passenger jet is not here yet, but the technology required to build it is beginning to move out of laboratories and into the air. The Concorde proved passengers could cross the Atlantic at twice the speed of sound. But Mach 5 is not simply Concorde with more powerful engines. It is a completely different category of flight. At ordinary airliner speeds, the atmosphere is something the aircraft moves through. At hypersonic speed, the atmosphere becomes a structural load, a heat source, and part of the propulsion system, all at the same time. The air can no longer move gently around the aircraft. It is compressed through powerful shock waves. Pressure changes violently. A thick, energetic boundary layer forms across the surface, and part of the aircraft's enormous kinetic energy is converted into heat. That distinction matters. Calling it friction makes the problem sound as though the air is merely rubbing against the aircraft. The reality is more extreme. The aircraft is compressing the atmosphere so aggressively that the air surrounding its nose and leading edges becomes intensely hot, and the heat is not distributed evenly. The broad surfaces are difficult, but the sharp surfaces are lethal. The nose, the engine inlet, the leading edges of the wings. These are the locations where airflow is compressed most aggressively, and where a tiny section of structure may be forced to absorb an extraordinary amount of energy. That creates the first paradox of hypersonic passenger flight. The aircraft needs sharp edges to control the airflow efficiently, but sharper edges concentrate more heat. Make the nose too blunt, and drag increases. Make it too sharp, and it may not survive. At Mach 5, aerodynamics and thermal management are no longer separate engineering problems. They become the same problem, and solving one can make the other worse. A conventional airliner relies heavily on lightweight aluminum alloys and carbon fiber composites. A hypersonic aircraft needs a far more complicated material map. Titanium in one region, nickel-based superalloys around another, ceramic matrix composites where temperatures become extreme, potentially carbon-carbon structures around the most heavily loaded edges. There is no single miracle material capable of building the entire aircraft. Instead, engineers need a carefully designed patchwork, in which every section is built for a different temperature, pressure, and mechanical load. But surviving the highest temperature is only part of the challenge. The aircraft must survive the journey from cold to hot, and then from hot back to cold. Every flight becomes a violent thermal cycle. The skin expands. The internal frame expands at a different rate. Engine ducts move. Fasteners stretch. Clearances that were perfect on the runway may change while the aircraft is traveling at hypersonic speed. The structure has to be allowed to move. Panels cannot simply be locked together as though the aircraft will remain one fixed shape. Joints may need to slide. Seals must remain closed while the structures around them grow at different rates. Control surfaces must continue moving, even when the surrounding airframe is no longer the exact same size it was during takeoff. The aircraft cannot merely be strong. It has to remain predictable while deforming, and that becomes much harder when there is a pressurized passenger cabin inside it. The hot outer structure wants to expand. The cabin pressure pushes outward. The cold fuel system creates another thermal zone entirely. The aircraft is not one structure operating at one temperature. It is several incompatible environments forced to travel together at more than a kilometer every second. And this is where engineers reach for one of the strangest solutions in aviation. They turn the aircraft's fuel into part of its cooling system. A passive heat shield can work for a spacecraft because re-entry heating lasts for a limited period. Some spacecraft even use ablative materials designed to burn away, carrying thermal energy with them. A commercial airliner does not have that luxury. It cannot return after every flight missing part of its skin. It has to land, be inspected, refuel, and fly again. So instead of simply blocking the heat, a hypersonic aircraft may need to transport it. Before the fuel reaches the combustion chamber, it can be circulated through passages around the hottest parts of the engine and airframe. The fuel absorbs thermal energy. The structure becomes cooler. The heated fuel is then sent toward the engine, where it can be burned to produce thrust. In principle, the aircraft uses the same substance that powers its flight to prevent that flight from destroying it. It is an elegant engineering loop, but it creates a dangerous dependency. The pumps must keep working. The cooling channels must remain clear. The fuel cannot break down unpredictably and leave deposits inside narrow passages. A small reduction in flow can create a localized hotspot. That hotspot can distort the structure. The distortion changes the airflow. The altered airflow creates even more heating. A minor cooling problem can become a feedback loop. Heat produces deformation. Deformation produces more heat. And because the aircraft is moving so quickly, the system has very little time to respond. On a conventional aircraft, cooling protects the engine. On a hypersonic aircraft, cooling may protect the entire vehicle. The thermal management system cannot be treated like a secondary component. It becomes as critical as the wings. Because on a true hypersonic aircraft, the cooling system is part of the airframe. The airframe shapes the airflow, and the airflow is part of the engine. Now we reach the detail most hypersonic concept art carefully hides. The engine capable of carrying the aircraft at hypersonic speed may not be capable of getting it off the runway. A ramjet or scramjet depends on the aircraft's forward motion to compress incoming air. At a standstill, there is not enough airflow. The engine effectively has nothing to work with. It needs the aircraft to already be traveling extremely fast. That is why many historic scramjet experiments did not take off from runways under their own power. They were carried into the sky, accelerated using rockets, and released only after they reached the speed required for the hypersonic engine to operate. Those tests proved something extraordinary. An air-breathing engine could produce thrust at hypersonic speed, but many of those powered tests lasted only seconds. And this is the real gap modern engineers are trying to cross. Not from Mach 9 to Mach 10, from seconds to dependable operation. From an experimental vehicle that flies once, to an aircraft that can take off, accelerate, cruise, slow down, land, and do it again. One possible answer is a turbine-based combined cycle engine. At lower speeds, the aircraft operates more like a conventional jet. A turbine engine provides thrust for takeoff and initial acceleration. As the aircraft moves faster, the airflow begins to shift. The turbine is gradually bypassed. A ramjet or another high-speed propulsion cycle takes control. But that handover is one of the most difficult moments in the entire flight. Two propulsion systems, sharing one inlet, operating under completely different conditions, passing control from one to the other while the aircraft is already traveling faster than almost any traditional air-breathing vehicle in history. If the airflow becomes unstable, the engine can lose thrust. If combustion moves into the wrong part of the duct, pressure can surge forward. If the inlet geometry is even slightly wrong, the engine may effectively choke on the air it needs to breathe. The engine has to capture a violent stream of air, compress it, inject fuel, ignite that mixture, and extract useful thrust before the air disappears through the exhaust. It is like trying to keep a match burning inside a hurricane. Except the hurricane is moving faster than sound, and the lives of every passenger depend on the flame remaining stable. But even solving the heat in the engine does not create a passenger aircraft. It creates a fast, experimental machine. An airliner faces a much harsher standard. It must tolerate failures. Its critical systems need backups. The cabin must remain pressurized at altitudes where the atmosphere outside cannot support human life. And its occupants need a realistic path to survival when something goes wrong. An experimental vehicle can accept risk. A commercial aircraft has to control it. One cooling pump may not be enough. One flight control computer may not be enough. One path for fuel, hydraulic pressure, or electrical power may not be enough. But every redundant component adds mass. Mass demands more fuel. More fuel increases takeoff weight. A heavier aircraft needs more lift and more thrust. That may require larger wings and larger engines. The most difficult part of the passenger experience may not be making Mach 5 feel comfortable. It may be proving that the cabin remains safe after hundreds of extreme heating cycles. Because aviation authorities will not certify a concept drawing, they will demand evidence, repeated tests, predictable failure modes, inspectable structures, and proof that the aircraft can survive problems its passengers may never even know occurred. Now, suppose engineers solve everything. The skin survives, the cooling system works, the engine transitions cleanly, the cabin remains safe, the aircraft lands intact. There is still one final wall: economics. A hypersonic passenger aircraft would require specialized materials, unusual maintenance procedures, highly trained crews, and an enormous amount of energy. Its value would come almost entirely from speed. That means it only makes sense on routes where the time saved is valuable enough to justify the cost. Los Angeles to Tokyo, New York to London, London to Sydney, not Chicago to New York, not Toronto to Montreal. Traditional aircraft will remain more efficient, more flexible, and far less expensive for the overwhelming majority of passengers. Then there is the sonic boom. A supersonic or hypersonic aircraft creates shock waves that can reach the ground as explosive noise. That may prevent it from using its full speed over populated land. The aircraft could be forced to climb and accelerate only after reaching open water. That reduces the number of routes where the technology makes sense. So hypersonic travel is unlikely to replace conventional aviation. Something closer to an airborne time machine for the people and cargo valuable enough to justify it. And that may be how hypersonic passenger flight begins. Not with millions of tourists, but with governments, emergency logistics, high-value cargo, military operations, and eventually, a small number of passengers paying not merely for a seat, but for the hours of their lives the aircraft gives back. Picture the first commercial flight. The aircraft has climbed above most of the atmosphere. The blue has drained from the sky. Far below, the Pacific appears motionless, but the aircraft is traveling faster than a rifle bullet. Outside the cabin, shock waves control the airflow. The structure is expanding under heat. Fuel is absorbing thermal energy before being burned. And an engine with almost no resemblance to a conventional airliner is using the aircraft's own velocity to compress the air it needs to survive. This is what makes hypersonic passenger flight so difficult. There is no single breakthrough that suddenly makes it possible. Not one engine, not one composite, not one cooling system, Every part must function as part of one tightly connected thermal machine. The nose shapes the shock wave. The shock wave feeds the engine. The engine controls the speed. The speed creates the heat. The fuel removes the heat. And the airframe must carry all of it while protecting the people inside. The 100-passenger Mach 5 airliner remains a vision. That distinction matters, because pretending the aircraft already exists makes the story less impressive, not more. The real achievement is that engineers have begun isolating the impossible parts and proving them one at a time. None of that guarantees a passenger aircraft will succeed. The economics may fail. The sonic boom may remain unacceptable. A vehicle that does not merely resist the atmosphere, but uses shock waves, heat, and velocity as working parts of its design. The hypersonic passenger jet is not real yet, but the engineering that could make it real has already left the ground.